Sanırım yayındayız. Evet, arkadaşlar sesim geliyor mu? Geri bildirimlerinizi duymak isterim. Evet, fonksiyonel programlama İstanbul'un 3. etkinliğine e, başlamak üzereyiz. Yayına daha yeni girdik. Belki 1-2 dakikayı geçirmekte fayda var. İnsanlar bağlanıyor muhtemelen. Umarım büyük bir e, kalabalık bir kitle ortaya çıkacak. Harika. Konuğumuz hazır bu arada. Ben bir iki dakika bekleyip belki e, bir iki dakika konuştuktan sonra kendisini hemen e, yayına alıyor olacağım. İstenmeyen bazı seslerin yayına gidişine engel oluyorum hemen. Güzel. Uzun süredir bir etkinlik yapmamıştık bu arada. Zaten ilk etkinliğimizi pandemi önlemlerinden önce yapmıştık. Benim de çalıştığım Pisano'nun ofisinde yapmıştık. Oldukça da güzel bir katılım olmuştu. Gerçekten motivasyonumuz oldukça yüksekti. Bir sonraki ve diğer daha sonraki etkinlikler için. Daha sonra araya pandemi girdiğinde ister istemez bir yavaşlama yaşadık. Arada bir canlı kodlama e, bazlı bir e, etkinlik daha gerçekleştirdik. Onun üzerine e, baktım bayağı bir zaman geçirmişiz. E, Neredeyse 3 ay olmuş yanlış hatırlamıyorsam. Ama tekrar aktif dönemimize dönmeye çalışıyoruz. Bugün bize konuğumuz Anjana Vakil. Kendisi lambda kalkülüs üzerine bir sunum gerçekleştirecek. Ben de bir yandan dediğim gibi o yayının ilk birkaç dakikasını geçiriyorum ki toplananlar toplansın, onlarla yolumuza devam edelim. Bu arada e, bu etkinliğin sonrasında da devamında neler yapacağımızı da ufak ufak konuşuyoruz. Geçtiğimiz günlerde sektörümüzdeki kadınların temsiliyle ilgili Twitter ortamında genellikle çeşitli tartışmalar yaşandı, döndü. Bunun üzerine biz Fonksiyonel Programlama İstanbul olarak Pisano'nun da desteğiyle e, bu konu üzerine bir şeyler yapmak istediğimizi söyledik. E, Bu anlamda da kadın yazılımcı gruplarıyla iletişime geçtik. Bu etkinlik sonrasında en azından biz kendi gücümüz dahilinde, kendi birazcık ilgi ve uzmanlık alanımız dahilinde fonksiyonel programlama e, birazcık çerçevesinde bu konuda neler yapabiliriz? İlgili gruplarla da konuşup istişare edip faydalı olmaya hep birlikte çalışacağız. Onun da bilgisini vermiş olayım. Şimdi çok da fazla dediğim gibi bekletmeden Anjana'yı da yayına alacağım. Ondan sonra zaten o kendisini tanıtacaktır. Ben kendisini 2016 EuroPython etkinliğinde, Rimini'de izleme fırsatı bulmuştum. Gerçekten çok eğlenceli ve güzel bir sunumdu. Ve Lambda Calculus'un fonksiyonel programlama ve genel olarak programlama anlamında e, o temel teşkil etmesi ben ilk fark ettiğimde büyük bir aydınlanmaydı benim için. Dolayısıyla ben oldukça heyecanlıyım. Anjana da bu konuyu gerçekten çok güzel anlatıyor. Bugün bu konuyu bize JavaScript üzerinden daha ziyade e, anlatacak. Şimdi dediğim gibi artık asıl etkinliğin kıymetli, değerli kısmına başlayabiliriz. Yeah.
Hi everybody. Hope you can see and hear me okay. Hello. So excited to be here. I wish my Turkish were better so that I could speak to you all and understand everything that Zakaria just said. But yes, hi, I'm Anjana Vakil. I'm a developer advocate at Observable. I love functional programming. I love speaking about functional programming, and I love speaking about functional programming at meetups like this because we can have a real participatory and kind of community chat about what I think is one of the coolest things ever in computation, the lambda calculus. So today I want to take you all with me on a little live exploration of the lambda calculus, and we're going to look at what that is or what that means. But because it's something so foundational for functional programming, and it's a very simple abstraction that gets incredibly complex in terms of what you can do with it. So for me, it's just a really exciting thing in the world of functional programming. And I am so excited to be here. So thank you so much, Zakaria and FP Istanbul for having me. And we're going to dive in. But I want you all watching and chatting in the chat to know that this is not, I'm not just going to be talking at you. I need you all to help me out here. So we're going to be doing this together. So Zakaria, if it all sounds good, I will just share my screen and launch in.
Yeah, you are
great
on the wheel.
Awesome, awesome. So let's see, this should hopefully work. So hopefully you can see my screen now. Excellent.
Yes.
All good. Okay, great. Just it's so hard in these modern times, everything virtual, just making sure we're all on the same page, literally. All right. So I want to talk to you about how we can build the entire universe of computing from a single arrow, by which I mean a JavaScript arrow function. So what we're going to be doing is diving into the lambda calculus using anonymous functions in a programming language that some of us maybe use every day, JavaScript. So the lambda calculus, first of all, what is it? What am I talking about? I've said lambda calculus like 10 times already. What am I even referring to? So when I see lambda, it refers to this Greek symbol lambda, which you might recognize as being the logo of every functional programming conference or language or meetup like FP Istanbul ever. I think we have lambdas all over the functional programming world. And that all is in reference to the lambda calculus. So the lambda calculus is a mathematical formalism, and it's all based on the notion of these small, pure, anonymous functions called lambda functions, which we're going to talk about more in a second. And this is a formalism that was developed like quite a long while before we got our fancy computers that we're used to using today. So Alonzo Church, amazing mathematician and logician and thinker of our kind of founding fathers of computing here, started developing the lambda calculus in 1932-ish and continued working on it. And he and many other people kind of continued elaborating it over the years. And what he came up with, it turned out to be, so it started as an investigation into the principles of mathematics. And what later was established is that this actually gives us a universal model of computation. So with the lambda calculus, which as we'll see is like founded on very simple principles, you can do anything that a Turing machine can do. The lambda calculus is equivalent to a Turing machine. So that's pretty cool. And even more cool is, since it's got functions at its heart, this is really the formalism and the abstraction on which all the world of functional programming is built. So for all of us here who are enthusiasts of functional programming, if you've never taken a look at the lambda calculus or tried to play around with it, I think it's a really great way to really explore some of those abstractions that are foundational for the whole paradigm of functional programming. And by exploring the lambda calculus, at least for me personally, I think it's a great way to get your mind into the mindset of functional programming, of doing everything with functions. So yeah, let's make things a little bit more concrete here. So a lambda function is kind of like an anonymous function in programming languages, like an arrow function in JavaScript or a lambda function in Python or something like that. They're both anonymous functions. They don't have names, but there are some differences. So first and foremost, the lambda functions that we're going to be talking about here, we're going to be doing them in a programming language, but primarily these are for thinking. These are for reasoning about mathematics and logic and computation, whereas we're used to using things like arrow functions or anonymous functions like Python lambdas for programming, for just like practical doing stuff in a programming language. So there's a different objective with these two. There are also some differences in terms of the mechanics of how these work. So in a language like JavaScript, an arrow function can take 0 arguments, it can take multiple arguments, and likewise, it could return a single value. It might not return anything, just return undefined. It might return some kind of complex data structure. So the inputs and outputs for an arrow function are kind of up to us. But in the lambda calculus, it's much more strict. You only get one input to each function. That's like every function you have can only have one argument. We're going to talk in a moment about how you make that work. And each returns exactly one thing. So this is really like the quintessential pure function. It takes one input in and returns one output out. And it does no side effects. So a side effect is anything that a function might do other than returning its output based only on its input. So in JavaScript, for example, an arrow function could do all kinds of side effects. It could log something to the console, or it could update a database somewhere, or it could render something on the page visually. Who knows? But in the lambda calculus, lambda functions can't do that. They can only return their outputs based on their input. That's it. No side effects, totally pure functions. So the game that we're going to be playing today is, if we treat a JavaScript arrow function like the pure single argument, single output lambda function, what can we build with it? And spoiler alert, I've already told you, we can build everything, literally anything we can compute with a single lambda function. Well, a bunch of complex lambda functions nested all within each other, but we'll see how that works. So yes, exactly. So somebody mentioned in chat that purity is not enforced in arrow functions. The language is not going to help us with this. Instead, we're going to play this game ourselves. We're going to constrain ourselves. We are going to force ourselves to write these functions as if they were lambda functions. Now, just as a warning, we are here to explore the mathematical beauty and the functional programming awesomeness of the lambda calculus, and to do some learning and to do some experimentation and hopefully try out a way of programming that we haven't maybe tried before. But we are not going to be using anything that we do today in our jobs anytime soon. The lambda calculus is really beautiful. It is not great for practical, like pragmatic programming. That's what all of the fancy functional programming languages built on top of the core abstraction of the lambda calculus are for. But today we're just going to be exploring this like from a perspective of learning and hopefully bending our brains a little bit. And we're not going to be learning anything relevant for our day jobs as programmers. So just letting y'all know about that. Okay, so let's dig in a little bit to the syntax of these functions. So in the lambda calculus, you see a lot of writings like this. So the syntax of a lambda function, and this is what's called function abstraction, or we could think of it like defining a lambda function. The syntax in the lambda calculus is you have the lambda symbol, then a variable like the argument for your function, the input for your function, in this case, let's say x, and then a dot. And everything to the right of the dot is like the body of the function, which is also in the lambda calculus, since it's a pure function, is the same as the return value of the function. So we have the input on the left of the dot, followed by or after the lambda, and then the output to the right of the dot. So this is like a little identity function. It just takes in a value x and returns x out. Now, the way we would write the equivalent in JavaScript arrow syntax is we're going to have the input variable x, then the fat double arrow, and then on the right-hand side, the return value of the function. So in this case, just for the identity function, we just return x. Now, we could put parentheses around the input value here, but we're not going to, just because otherwise we'd be writing a lot of parentheses, let me tell you. So we've said that a lambda function only gets one argument. And if you are anything like me, that immediately raises the question, well, then how do I do anything? Because we need to sometimes operate on multiple pieces of data at the same time. So the way that we sort of fake that in the lambda calculus is we take in the first argument, like x here, and then we return to the right of this dot here, we return another function that takes in the second argument we need, in this case, y, and that function returns whatever the operation is on both of them. So in this case, to do an addition function, we'd abstract or define a function that takes in an x, returns another function that takes in a y, and that inner function returns x plus y. So this is a little bit weird, especially when we translate it to JavaScript. Now, in JavaScript, as we've said, there are no restrictions like this. So we could have a 2-argument arrow function that takes in x and y with parentheses and commas separating them, and then just returns x plus y. But since we're forcing ourselves to play this little game of pretending that arrow functions are lambda functions. So instead, we're going to write that like this. We're going to have an arrow function that takes in x, and that's going to return another arrow function that takes in y, and that second arrow function will return x plus y. Everybody on board here? I can't see any of you, so I'm going to rely a lot on the chat to make sure that people are with me. And if you have any questions or things like that, please feel free. All right, so unless anybody stops me, I'm just going to keep going. I miss seeing all of your faces. All right, anywho, so now we know how to define or abstract functions, how we can do function abstraction, and how we can even create functions that sort of take in multiple arguments. So now let's talk about how we can actually use a function. So in the lambda calculus, this is called function application. In programming terms, we'd probably call that calling the function. So how do we call or apply a lambda function? Well, in the lambda calculus, it works like this. You take the function, like our little addition function here, and it might have parentheses around it. And then there's a space, and then the argument that it's to be applied to. And in this case, we are going to ultimately take in 2 arguments, this x and y. And so what we're going to do is have a space and then the first argument, and then another space and the second argument. And so the way this works is that 5 now, this function will get applied to 5, which gets passed in as x, which returns a function that takes in y and adds 5 plus y. And then that inner function, that y function, is going to get applied to 1, which essentially does 5 plus 1, which gives us 6. Okay, if this feels weird, that's okay. It's just because the lambda calculus is a little weird. Now, the way that we're going to do that in JavaScript is we don't use spaces to apply things in JavaScript. We use parentheses. And this is valid. It's going to feel a little strange, but what we're going to do is take our function, wrap it in parentheses, and then immediately after that, call it on the first argument. And so that whole thing here is this 5 is going to get passed in as the x, and that's going to give us a function that takes a y and adds 5 to y, And that is going to then get called on 1, so that again, we get 5 plus 1, we get 6. So this is just the weird little syntax tricks that we're going to do to pretend that JavaScript is the lambda calculus today. Hopefully everybody is on board with this weird little game that we're playing. If questions come up, we can definitely talk about it. Either you can ask in chat, or we'll have some time at the end, hopefully, to talk through it. Okay, so let's see what we can do now that we've figured out how to define functions or do function abstraction, and how to apply functions or call functions. Okay, I said that we can do anything in computation. Let's start somewhere simple. How about numbers? Programmers like numbers, right? Everybody likes numbers. I like numbers. Counting is fun. 1, 2, 3, 4. I wish I could count in Turkish. I can't. I will have to work on that. But in this world, so far, we only have functions. All we have, the only item in our universe, is a single argument, single output function. So what can we count if all we have are functions? I'll let you think about that while I drink some water. So all we know how to do is define functions and call functions. How about we count applications or calls to a function? This is going to feel a little bit weird, but we're going to start thinking about numbers. And I'm talking about whole numbers, so positive integers here. We're going to think about them as the number of times that we call a particular function. So let's try to do this. Let's try to make us some numbers. So we can make some initial numbers like 0, 1, 2, 3. Why don't we start out with 1? Because that's usually a good place to start. Okay. A number is going to be, in the lambda calculus, is going to be, like everything else in the lambda calculus, a function. The question is, what shape of function is it going to be? So just by caveat, we're going to get used to this, but it's going to feel weird at first. A number is going to be a function that takes in another function. I'll call that other function f. So we have an arrow function that takes in an f. And then that's going to return a function that takes in some value, x. And it doesn't really matter what that value is for right now. It's going to take in some value. And what this number function is going to do is it's going to call f on x a certain number of times. So in the case of 1, it's going to call f once on x. So the number 1, the integer 1, is going to be a function that takes in an f function, takes in some value x, and calls f once. And then you can probably guess what 2 is going to be. This is going to have the same shape. It's going to be a function that takes in an f, which gives a function that takes in an x. And it's going to actually call f not once, but twice on x, if I can get my parentheses right. So 1 will call f once, 2 will call f twice, 3, same thing. F of x, so it'll call it 3 times. See if I got those parentheses matched there. And so then we can even do 0 is going to take an f, and that's going to take in an x. And this one is, and I would love to, for if anybody can guess what the right side of this 0 function should be, but I think there's a little delay on the stream, so maybe this is tricky. Any guesses what the right side of, or the output of this 0 function is going to be? If 1 calls f 1 time and 2 calls f twice, we want to call f 0 times, exactly, so we want to just return x. Bingo, fabulous. Awesome. See, look at this. Even in the virtual age, we can do this together. Okay, so now I'm telling you that these things are numbers, but right now you have no good reason to believe me. Because I don't know about you, but this doesn't look like a number to me. This looks like some weird function that's like nested with another function. And how do we actually know that these are numbers? So what we're going to do is cheat a little bit. And we're going to make a number converter function called toNumber, which is going to convert our lambda calculus numbers into JavaScript numbers, that like integers that we can see, or JavaScript number primitives that we can see. So I'm going to make this toNumber converter. It's a function that takes in a number n, a lambda numeral n, and then is going to apply that numeral n. Remember that all numbers n, they take an f and an x. So what we're going to use for f here is a little function that takes some integer and adds 1 to it. And we're going to start out with the x being 0. So the idea is if we call this I function 0 times, I should get 0. If I call it once, I should get 1. If I call it twice, I should get 2, etc., etc. Are we convinced? Does that seem reasonable? Everybody on board? All right, let's try it out. So if I did this right, which is a big if, I should be able to take my numeral 2, which I defined on the last slide, and convert it to a number and get 2. Huzzah! Wonderful. And I should be able to do this with all of the other numbers that we have defined so far, even 0. Got to check those edge cases. All right. So hopefully I've convinced you now that we've got something numberish going on here that we can convert to JavaScript numbers to convince ourselves. All right, so now we've got some very basic counting going on. And what we've just done is we have implemented what are called church numerals, named after our good friend Alonzo Church, father of the lambda calculus. So if you want to DuckDuckGo something to find out more about this, you can DuckDuckGo the term church numerals. So this is how we're going to do numbers. Now that we've got some numbers, how about we start doing something with them? Let's do some arithmetic, huh? Some kindergarten math in here. So now we've got these numerals. Let's say that we have 2 of them, n and m. One we'll call n, one we'll call m. And we want to add them together. Let's pretend that n is 2 and m is 3. How do I add those together and get 5 if all of that these numbers do is basically count applications of a function? I'm going to let you ponder that one while I take another sip of water. So what we're going to have to do if we want to get to 5, and we've got a 2 and a 3, we want to take whatever that function is, f, that each of those is counting, and we want to call it n times, so 1, 2, and then we want to call it m more times, so 3, 4, 5. Okay, it's hard to do with my fingers, but you get the idea, hopefully. So we're going to want to call a function n times and then m more times in order to get our addition function. So let's implement a function called add. And this is going to take in 2 numerals, an n and an m. And by now, hopefully, we're used to these, like we're pretending that we have these multi-argument functions here. So what we're going to do is we're going to take in an n and an m. And then we want to return another number, right? Another numeral. And by now, we're used to the shape of these numerals. It's f into an x. Now, first of all, we have to call this f function n times. And we do that by applying n to f and then f to x. That's how we would get n. But we also still want to call f m more times. So what we want to do here is take the output of this function, of this application, wrap that up. This is going to become our new x, the value on which we then call f m more times. So if this feels super weird, that means we're doing it right. Let's just recap what's happening here. N applied to f applied to x, as we saw previously, is going to call f n times. So if n is 2, this is going to call f 1, 2 times. Then, whatever the output of that is, in this case, 2 calls to f, we're going to treat that as our new x, and we're going to apply m to f to x, to our new output here, so that f now is going to get called m more times. So if m is 3, then we get 3, 4, 5 total calls of f. Okay. This probably sounds super weird, and you're probably like, Anjana, I don't even believe you. So let me try to convince you. If this works, then we should be able to create a numeral like 4 by calling add on 1 and 3, for example. So n would be 1 and m would be 3. Now, if that works, then I should be able to convert 4 to a number and get 4. Oh my gosh. Okay, but maybe you're not convinced. Let's try it with some more cases. How if I add 2 and 2? Does that also work? Okay, and let's see if it works with my original example, 2 and 3. Ah, 5. And shall we test out an edge case? Let's try adding it to 0. Ooh, I don't know what's going to happen. I could have messed it up. Oh, whew, it even works with 0. Okay, so are we convinced? We have addition here. We have an addition operator. Yes? Hopefully, again, there's this little lag here, so I can't see what everybody's saying, but hopefully we are all slightly convinced that this weird thing right here is actually a way to add 2 church numerals together. Okay. Let's see what more arithmetic we can do. How about multiplication? So now that you've seen how addition works, I'm going to give you a minute to think about how multiplication might go, while, again, I continue hydrating. Great. Convinced and blown away. Fabulous. All right. Now let's see. How if we can add n and m by continuing to make calls to f, how can we multiply n and m? All right, so let's continue to suppose that n is 2 and m is 3, just for sake of example. Make sure I'm in the frame here. Okay. If we want to multiply 2 times 3, we sort of have to call the function n times, so like 1, 2. But then we want to do that whole multiple application thing m times. So we want to do 1, 2, that's our first time. 3, 4, that's our second time. 5, 6, that's our third time. Yeah, we're basic kindergarten math here. But so we want to call the function n times, and we want to do that m times over. So that is what we're going to try to do in our multiplication function here. I'll make a little function called m. And yeah, we sure are close to Peano axioms. We're not going to talk explicitly about that, but you are absolutely on the right track here. Okay, so a multiplication function is, again, it's going to have a similar shape to our addition one. It's going to take in 2 numerals, n and m, and then it's also going to return a numeral. So that's going to be of this function, this f to x shape. And first thing we need to do is call n times. So what this is going to do is, like, let's say, so if n is 2, this is going to call f of x, right? Now what we want to do is do this thing, the 2 calls to f, m times. And what this does right here, this first application, this gives us a function that calls f n times. If only we had a way to call that function a certain number of times. Oh, wait. That is what numbers do. They take a function and they call it a certain number of times. So what if I take this application of n to f and I treat that as the f which I'm going to apply m to, so that m will now be applied to this function that applies f 2 times or n times, and that will create a function that does this 3 times, if m is 3, on x. Huh? So if I did this right, if I did this right, we should be able to call multiply, this mul function, on 2 numbers like 2 and 3 and get their product, 6. Oh my gosh. Wait, let's make sure I'm not lying to you here. Let's try it with different numbers. 3 and 3 gives us 9, 3 squared. What about 1, huh? Ah, that works too. And shall we again try the really tricky edge case? I don't know. Let's see what's happened. I could have messed it up. Let's find out. Oh my gosh, it even works with 0. Y'all, I don't know about you, but this feels like we're doing magic here. So what we've done is we've by remembering that everything is a function and we can treat anything like a function, f, we're starting to get into the mindset of once everything is a function, you can get real tricky with how you're passing functions in and out of your other functions. Whew. So we've got a multiplication function. We've got an addition function. We're starting to figure out the mechanics of working with these lambda numerals, church numerals, excuse me. Okay, let's press on, shall we? One more arithmetic question for you. How do we do n to the power of m? I'll let you think about it. Okay, n to the power of m. Well, let's sketch out our structure here. So this is going to also take an n and an m, and it's going to take it's going to return a numeral, which is of this shape. Okay, so if I want to raise n to the power of m, what I'm doing is I'm multiplying n by itself m times, right? So if I want to do if n is 2 and I want to raise it to the power of 3, this would be something like 2 multiplied by itself 3 times, yeah? Okay, let's see if we can figure this out. So, and this is going to be, we're going to do this together. Let's see if we can even do it right. So first of all, we always need to start off with applying n to f to x. This gets us 2, if n is 2. Now, the application of n to f is what we're going to want to do m times. We're going to kind of want to multiply n times itself m times. So what we can do is instead of treating the application of n to f as the function that we want to apply multiple times, it's actually the numeral n that we want to create a function that applies that m times to this function f and then to the output. And I could have done this wrong, so let's find out if I did. If this works, I should be able to use this pow function to raise 2 to the power of 3. Let's find out if we get the right answer. Oh my gosh. Okay, that was legit stressful. So I can raise 2 to the power of 3 using my power function. And let's just test it out. 2 to the 2 is 4, and 2, we have 4, right? 2 to the 4 is 16. Okay, cool. Now, here's if this hasn't blown your mind yet, wait for this part. Okay, so you see how here we've got this application of m to n, and then we're taking that and applying that to f and applying that to x, right? In our numeral function, which takes in an f and takes in an x. But taking in an f and applying it, taking in an f and taking in an x and applying itself to f and x, that is just what numerals do. So we could actually simplify this. We don't even need this f and x part. We can take this out and take this out, And the power function actually becomes this super simple m applied to n in the lambda calculus. And as we can see here, it still works. So is that wild or what? This is like the easiest function, seems like easier than addition even, thanks to the way that these functions, these numerals work out. And let's try the really tricky edge cases again. Let's see if it even works. Raising to the power of 0 should always give me 1. It even works for that. So like we've got real math here, people. Isn't that exciting? I don't know. I think it's really exciting. So hopefully this feels super weird, but also a little bit exciting. And yeah, and as Xenia says, give us lambda calculus and we shall move the world. It is the only fulcrum we need. Okay, so now we have done some really advanced computation. We made some integers and we made some very simple arithmetic operators. And it might not seem like we have a lot of capabilities so far, but we can already solve some very hard problems. Like, for example, we can think deep thoughts, including the answer to life, the universe, and everything. Don't know if anyone has read the book, The Hitchhiker's Guide to the Galaxy, but if we use only the small tools that we've got so far, all based on a single little arrow function, then we can figure out that the answer to life, the universe, and everything is, if you add 2 to the multiplication of 4 times the multiplication of 2 times the addition of 4 and 1, then you get an answer of 42. Huzzah! Don't know if there's any Hitchhikers fans out there in the audience. Yes, okay, I think a couple folks. Woohoo, spoilers. No, that's all good. That's all good. But yeah, this is, we've already got enough computation to solve the answer to life, the universe, and everything. So pretty cool, huh? All right, I'm gonna let that sink in for a moment. Let's think now that we've got some simple math, we've got some simple numbers, we've got some simple arithmetic. We're not going to do the rest of math. We could totally do much more math, as we said, but for the sake of programming, let's move on and think about some other stuff that we might need to write computer programs. What else do we need? I'll give y'all a second to think about it. Okay, any suggestions of what else we need? I'm looking at the chat. Any suggestions of other stuff that we need to do programming? We need inputs and outputs. Yes. Okay. That's gonna be super advanced, late lambda calculus we're not going to get to today. But we can also do some things that we definitely need, like control flow. How about conditions? Yeah, how about some conditionals, right? And like if else branching, right? If we want to do programming, we're probably going to need that control flow. So let's define some Booleans and some conditionals, because we really need both to go hand in hand in order to do programming. So we can't really have a conditional unless we have some concept of a truth value of like a Boolean. So we need to define these together. And we're going to basically define a Boolean, and like using JavaScript's ternary syntax, a Boolean is something which, if it's true, then we do something. And if it's false, then we get to hit our else case and we do something else. So we're going to define Booleans, true and false, and the concept of an if-then-else clause all together at once so that we can do some programming. Okay, so an if-then-else function, because everything is a function here, so we'll think of it as like a clause, but it's really a function here, is going to be something that takes three things, just like this JavaScript ternary syntax here. It's going to take in a Boolean, which I'll just abbreviate bool. It's going to take in some kind of then clause, like a then do. I'm just going to use this to avoid conflicting with the JavaScript name on else. So it's going to take a Boolean and a then thing and an else thing, and it's going to do something. Okay, we'll find out in a second. Now, I'm just going to comment this out for a second. Let's now think about how Booleans operate. So a Boolean is going to be something that when used in this if-then-else clause is going to put us down this then path. Yeah, a true Boolean. Somebody's asking why we're learning conditionals in a lambda calculus talk. Well, it's because we want to show that the lambda calculus lets us do all of programming. And in order to do programming, we need stuff like control flow, like these truth values and conditionals. So that's what we're looking into here. Okay, so a true value, which I'm going to name TROO true, just to avoid conflicting with JavaScript's true, is going to be something that when given a then clause and an else, it's going to choose the then clause. It's going to choose the first thing in this ternary, if it will. So true is just going to be defined basically as the thing which, when you give it a then and give it an else, it's going to choose the then. And similarly, false, which I'm going to call false, just to avoid conflicting with JavaScript's false, is going to also take a then and an else, but instead of choosing the then like true does, it's going to choose the else. So now, if we think about these Booleans as like choosers, we can go back to our if then else, and we can take our Boolean and apply it to the then and the else, and it will choose whichever one is appropriate for its truth value. Okay? So if this feels weird, it's because it's totally different than how we usually think about these things. But if when we start to think about in functional programming, and in the lambda calculus is the perfect abstract representation of this, when we think about a piece of data like a Boolean, what we really want to think about it in functional programming is not like what it is, but what it does, its behavior. So in this case, we're going to care about its behavior of how it chooses one of these paths down our branching statement here. Okay, now you have no reason to believe that any of this works. So let's try actually programming something in it. Let's say that today I am tired, because that is true. So I'm going to make a value called tired, and it is true. Now, the number of coffees that I drink today, because it's still the morning over here in San Francisco where I am, the number of coffees that I drink today is going to be determined by how tired whether or not I am tired. So if I am tired, then I'm going to drink 3 coffees today. Else, if I'm not tired, then I'm only going to drink 1 coffee. So what I've got here, this coffees today, is a little program, and it is a program which will tell me the number of coffees I need to drink today based on how tired I am, which in this case is true. I am tired. So let's find out how many coffees I should drink today. 3 or 1? It's going to be 3. Yay! We did programming. We wrote a program to tell me how many coffees to drink. And just to make sure that we're not, I'm not lying to you here. If suddenly I'm just so energized because I am so excited about the lambda calculus that I have this wave of energy and I am no longer tired, and tired becomes false, as soon as I update this, my coffees today number is going to update. So let's see what happens. It goes down to 1. So you see, we've got like working conditional logic here. Huh? Pretty cool, right? I think so. I don't know. Hope you do too. So we've got some basic control flow now with our Booleans. All right. Now, as we continue talking about Boolean values, it's hard to look at these functions and know what they mean. So again, let's just cheat a little bit. And let's make a 2 Boolean converter, kind of like our 2 number converter from earlier, that's going to take in a Boolean and it's going to apply it to JavaScript's true and false, so that if the bool is true with our O's, then we should get JavaScript true. And if the bool is false, then we should get JavaScript false. So let's just test that out. Okay, so now we can read the value of a Boolean, of a lambda Boolean as a JavaScript one. Okay, cool. On board? Hopefully we're on board. Okay, great. So now that we've got Booleans, guess what else we could do that's fun? How about some logic? Huh? Programmers, we like logic. Logic is our bread and butter. We live by it. So how do we make some basic logical operators? Let's try starting somewhere simple with negation. Now, if Boolean values are basically branch pickers that choose one of the two branches, and of then and else. How do we negate a Boolean? Let you think about that. While you're thinking about that, I'm just going to sketch out the shape of this function. So it's going to, the not operator is going to take in a single Boolean, and it's going to return another Boolean, right? And Booleans have this shape that we just discovered. They take a then and an else, and they pick one of them, right? Now, usually the Boolean, we're used to applying it like this, right? So we apply it to the then and the else, and if the bool is true, then it picks then, and if it's false, then it picks else. So how can we negate this Boolean? Any suggestions? Don't see any coming up in chat. Okay, so to negate this Boolean, we want, so if the Boolean is true, usually it picks then, but what we want is false. And so that means we want to go down the else path. So what if we just get really tricky and yeah, what if we just switch them? And we trick the Boolean into picking the wrong value, picking the opposite one. Huh? Just reverse them, exactly. Okay, so if we've done this right, then we should have now an operator, not, which I can call on a Boolean, like true, and get false. So not true becomes false, excellent, and not false should become true. Huzzah! We've got a logical operator, our very first logical operator. Amazing. And let's try to do, real quick, a couple more logical operators. How about or and? Okay, let's start with or. So we're a little short on time, so I'm gonna try to run through this. Or is gonna take in two Booleans, right? And I'm just gonna name them A and B. So if or takes in a Boolean A and a Boolean B, it's going to return a truth value based on the truth value of those two Booleans. So now so if a Boolean like A, it's going to be applied to two things, right? That's the shape of it. Now let's do some thought experiments. Okay, let's hypothesize that A is true. If A is true, do I care what B is for the or operator? No, right? I can just pick A. I can just return true based on the value of A because or will always be true if A is true. So if A is true in our hypothesis, it's going to pick this first thing here, and we want this operator to return true. So I want to put a value that's true there. And in our hypothesis, A is true. So let's put A there. So if A is true, it's going to choose itself, which is true, and return that as the value of the operation. Cool? Okay, now let's suppose the opposite. Let's suppose that A is false. If A is false, it's going to pick whatever is here. And if A is false, then we do need to look at the truth value of B in order to know what the value of the or operation should be, right? So if A is false, then whatever the truth value of B is, whether true or false, that's going to be the result of the or. So if A is false, it's going to pick this second thing here, this else position. So why don't I put B there, and then whatever the truth value of B, that's going to be the result of the whole operation. Huh? So let's see if this works. If I did it right, which again, big if, then I should be able to apply or to true and false like this and get true. Okay, but let's just try our truth table here. So, oops, that's wrong. So true and true gives me true. False and true should also give me true. And just to make sure I haven't hard-coded this to always return true, let's try false and false, and we get false. Yay! Yay, we did or. Okay, and so now for and, it's going to look very similar. And again, we're going to do our little thought experiment. Now, if A is true, with and, now we need to go on and look at the value of B. So if A is true, it's going to pick this first thing. And then whatever the value of B is, that's going to determine the logical result of the AND operation, right? So if A is true, let's have it pick the first thing here as B. And then whatever the value of B is will be the value of the operation. And by the same token, if A is false, similarly to how it worked up here, if A is false, we don't even care about B. We just want to return false immediately. So if A is false, it's going to pick what's over here. Let's put A there since it'll be false in that case. And we should get an operator, that gives us, what did I do here? Should get an operator that gives us, okay, here we go. The result of true and false should be false. The result of false and false should also be false, and so it is. The result of false and true should be false, and let's see if it works in the one case where we actually want true. Huzzah! We've got and or. Huh? Okay, I see a question in the chat. Can we give an example of inclusive and exclusive for or operator? So in this case, we're doing an inclusive or. So if either of them is true or both are true, then we're going to get true for the operation. Now, because we can do everything in here, we could also create an exclusive or operator, but we unfortunately just don't have time for that today. In fact, we don't even have time for everything I wanted to do today. I think we're running a little bit short on time. I wonder, Zachariah, can we get a time check? I want to see if we can keep going here. But in any case, yes, it is absolutely possible to build whatever logical operator you want, or whatever operator period you want, because you can do everything you can do with a computer with lambdas. And how weird is that, right? Everything just functions. Now, it might not be very simple, might take a lot of work and a lot of time and many years and many PhD theses to prove that it's true, but totally doable. So nobody is kicking me off stage right now, so I'm just going to keep going. So now that we've got some math and logic operators, and we've got some integer and Boolean data, what else might be useful for programming? How about some data structures, right? So if we start working with data, we're gonna, it's nice to work with primitives like Booleans and numerals, although these aren't even primitives in the lambda calculus. We only have one primitive, and it's the function itself, a lambda function. But once we want to start doing more complex stuff, we're probably going to want to start collecting that data. Start collecting that data into more complex clumps, which we will need some data structures for. So let's start by making some pairs. A pair is going to be two things, a left item and a right item. And I'm just going to write this out. We're not even going to do it together just because this is so weird. But a pair, just by convention in the lambda calculus, is going to be something which has a left item and a right item. It's going to take those when we're making a pair, we're going to take those in. And then the pair itself will be a function that looks like this. It takes in an arbitrary function f, and then it applies that function f to the left and right. And this is going to be useful later, but this is just by convention how we're going to define pairs in lambda calculus. Now, how do we get stuff out of a pair? Once we've put it into a pair with our make pair function, how do we get it out? How do we choose the left item? So if a pair is something that takes in a random function f, well, not random, but arbitrary function f, and then calls it on the left thing and the right thing, and if we want to get the left thing out, then we can create a little function called getLeft, which is going to take in a pair, and it's going to pull out the left item from that pair. And we already have a function that's actually really great for doing exactly this, for choosing between a first thing and a second thing. Yeah? We just made functions that are all about this, all about choosing one of these things, which is our Boolean functions. Our Boolean functions, when they're applied to one thing and then another, they will choose either the first or the second based on the truth value. So if I want to get the left thing, like how about I pass in the true function as my f here? And the way a pair works is when you call the pair, that's when you apply this function f to it. So I can make a get left function by calling the pair on our true Boolean. And similarly, I can make one for the right, to get the right element by calling the pair on false, which will choose the right one when applied to the pair. Yeah, great, exactly. Okay, so now if I've done this right, then if I make a pair out of 2 and 3, I should be able to call the get left function on that pair to retrieve the number 2. Let's see if it works. Okay, cool. And just to make sure I'm not lying that these work, let's try get right as well. And it gets us the right. Okay? Okay, cool. So now we're going to try and now take these functions, and I know we're a little bit at the end of our hour here, but if you bear with me, we can use this to actually build lists out of pairs. Okay, so bear with me. I'm gonna try to rush through this because we're a little over time, but if you have a few extra minutes, please hang out and let's do some list programming, huh? Okay, so what can a list contain? There are only so many options. A list could either be empty, so it contains nothing, which in functional programming parlance or lispiness is often called the nil list, nil. Or it could have one thing in it, or it could have more than one thing in it, multiple things, right? So I think that covers all of the cases of what lists can have, either nothing, one thing, or lots of things. So we're going to make lists as pairs where the left element of the pair is going to be a Boolean that indicates whether or not the list is empty. And then the right-hand side is going to be whatever the contents, the actual elements of the list are. See how this works. But the key part is we're going to have this left-hand element that indicates, is the list empty? Empty? True? False? So keeping in mind that a list has this form, empty and list contents, we are only going to have one list that actually has true on the left-hand side, and that's going to be the empty list. There's only one list that's empty. Every empty list is the same, and it's called, we'll call it nil. And if the list is empty, then whatever we put on the right doesn't really matter. So let's just use the value true. So let's make an isEmpty function that's going to figure out, given a list, whether it's empty. And the thing is, we don't even need to do this really because we already made a function that gets the left-hand side of a pair. And that's all that isEmpty is going to do. It's going to get the left-hand side of a list. So now to make our nil list, we're going to make a pair of true and then really whatever we want. But let's make the right-hand side true too, because we're not ever going to look at the right-hand side. So that's fine. So our nil list is now going to be the only list which we can pass to the isEmpty function and get true. So if we call isEmpty on our nil list, we get true. Okay, so we've got an empty list. Yay, we have nothing. Huzzah. Okay, let's now try to get lists with stuff in them. So how do I add something to a list? We can start from the empty list and then like add one thing, and now we've got our single item list. Yeah, sorry, I keep hitting my mic. Okay, so to add an item, we're going to want to prepend that item to the front of our old list. So we get a new list where now empty on the left is false. And then on the right-hand side, we have a pair with the new item and the old list. And the way this is going to work is like if we keep adding things to lists, we're going to have non-empty lists that end up like nested pairs. So this is going to look, it's going to feel pretty weird, but where we would be used to looking at an array or something, a listy like this of 3, 2, 1, this in the lambda calculus will look like a pair that has false on the left because it's not an empty list. And then on the right, we have this nested structure where we have like 1 prepended to nil, and then 2 prepended to all of that, and then 3 prepended to all of that. Okay. So to make this prepend function, we're going to take in an item and the old list, and we're going to make a pair of false because the new list is not going to be empty, and then a new pair with the contents of the new list, which is going to be a pair of the new item and then the old list. Okay? So this will prepend one item onto a given list. So for example, if I prepend 1 to the nil list, I get a single item list that looks like this. And if I prepend 2, if I prepend 2 to that single item list, I get a little list that looks like this. And if I prepend 3 to that, then now I get my like a complex, like a 3-item multi-item list. Okay? So yes, so lists are going to kind of be like these nested, weird little nested things. And that is how we're going to work with lists in the lambda calculus. Now, okay, so now we know how to put things into a list, but how do we get things out of a list? Once we can put things in and out of our data structures, then we should be pretty golden. So let's take a moment to consider how the structure of these lists looks. So we said non-empty lists have this form. There's a false on the left because it's not empty, and then the contents on the right. And we can think about those contents as being comprised of a head, which is the first item in the list, and then a tail, which is everything else. So for example, in our multi-item list that we just made, the head is going to be the item 3, and the tail is going to be this whole thing, the rest of the list, this other nested stuff. So what essentially the head is kind of like the outermost thing, and then the tail is everything else that's inside. Yeah? Hopefully y'all are with me. So the question is, how do we get the head and the tail of a list if they look like this? And then once we know how to do that, how can we get like an arbitrary item from the list? So let's find out. So a head, let's make a head function, which is going to basically pull the head of a list out, which is going to take in a list, and it wants to find, we want to find like this 3 here. So how do I do that? Well, first of all, I want to get the contents of a list, and we said that the contents of a list are on the right, right? So first we want to get the right-hand side of the list. That's going to be the contents, all of this. And then we want to pull out the first thing, right? So that's going to be the left-hand side, this head here, the left-hand side of that right-hand pair. So if I call get left on the right-hand side that I got out, I should get a function that pulls out the head of a list. Let's try it out. Let's try to get the head of our multi-item list. Oops. Okay, so we got out our 3. Cool. Now the tail, similarly function, is going to take in a list. And this time, instead of getting, we're still going to get the contents. So we want to get the right. And then instead of getting the left-hand side, we want to get everything else here. That's our tail. So we're just going to ask for the right instead of the left. Okay, so now we can use these 2 functions to pull out an arbitrary element. So let's aim for this 2 here. How do I get my 2 out of my multi-item list? Now, just for the sake of time and the delay on the chat, I'm just going to talk us through this. But if you're following along, just take a moment to think to yourself how we can do this. And we're going to, so what we're going to need is, first we need to get the tail of this multi-item list, right? Because the 2 is in there. So let's get the tail first. Now, once we've got the tail, we are going to want to take the first thing in that, which is going to be the head of the tail, if that makes sense. So if we call head on the tail of our multi-item list, we should get out our 2. Yay! So hopefully this demonstrates that we can now pull items out of our lists as well as insert them into them. So look at all of the stuff that we have got now. We've got data. We've got numerical data. We've got truth value data, Booleans. We've got arithmetic operators like add, multiply, and power. We've got some logical operators. We've got not, and, or. We've got control flow with our conditionals, thanks to our Booleans. And we've even got data structures with these pairs and these lists that we can put items into and take items out of. So we've got a lot of stuff, and we could actually write some like basic programs using this kind of thing. And what we've been doing, representing all this data and these operations this way, this is called church encoding. So another great term to look up if you want to. Church encoding is this process of encoding all of these things that we need to program in lambda functions in the lambda calculus. And it's named after our BFF, Alonzo. And church numerals, just to clarify, are kind of like one special case of church encoding. It's like one subset of church encodings. So if you want to read more about how we can do all kinds of other stuff, all kinds of other operators, because like there's so much more we could do. We could still do subtraction and division. They are way harder than addition and multiplication, but we could do them, just not in this time because I've already gone over. We could do like logical predicate functions. Like we had a little bit of one kind of with our is empty function, for example. But we could do like is even or is odd, things like that. We could do equality and inequality operators. We could even start working with strings by thinking about characters as like numeric codes, and then thinking about strings as just lists of characters now that we have lists. And to help us work with lists, we can build some list operators like map, reduce, and filter, our BFFs in the functional world. So, you know, we can do all of everything that a computer can do. Anything a Turing machine can do, we can do with the lambda calculus. So if you want to read up on how any of these other data structures or operators work, check out church encoding. The Wikipedia article on it is actually really great, and have some other resources for y'all here. The slides that we've been working through, what you've been seeing is an observable notebook. Observable is the company where I work, and we make these live, interactive, in the browser, living notebooks for programming and data visualization. And so you can check out these slides at observablehq.com/@Anjana/the universe in a single arrow. And there's some links in there which you can follow to read more about lambda calculus and church encodings. There's a great talk by Corey Haynes and the forthcoming book about lambda calculus that was, when I first saw that talk, that's sort of what inspired me to dig into lambda calculus. So please check that out as well. And I just want to thank you all so much for joining us and going on this weird, wild adventure into the world of lambdas today. Please feel free to stay in touch on Twitter. I'm Anjana Vakil. You can email me at anjana@observablehq.com. And thank you so much. Teşekkürler. It's been so great being here.
Anjana, thank you very much for your time and this great talk. To be honest with everybody, I did have a very similar talk like this just from Anjana like 4 years ago, and still this lambda calculus just keeps blowing my mind. It shows me, how come a simple thing like this can be this powerful. Like, you know, it's powerful as you can do whole computation with it. Actually, as computer programmers, we are just abusing this math thing because, you know, it precedes our computation theory. It is the computation theory, but it existed before any of the computers did exist.
Exactly.
So, yeah.
We can do computing without even computers, just by writing down these lambdas on paper. Is that cool? I think it's cool. Yeah.
Yeah. So, Anjana, again, thank you very much for your time. We were hoping to have you in Istanbul, but you know, the pandemic thing also changed a lot of things like this.
I know. Yeah. No accounting for that. But I hope to be able to travel to Istanbul sometime. So I hope to be able to see you all in person one day.
So thank you very much again and again.
Thank you so much for having me. And I'm sorry we went a little bit over. I don't know if anybody had questions or wanted to follow up. I have a few minutes, but otherwise you all know where to find me. So feel free to reach out. And yeah, hope you all have lots of fun digging into more lambda stuff.
Yeah. Okay. Then see you later.
Bye. Thanks again. Teşekkürler.
Yeah. Takip eden herkese çok teşekkür ediyorum. Birazcık süreyi aştık ama çok fazla da aşmadık. Gerçekten bence oldukça şaşırtıcı ve faydalı bir konuşmaydı. Üzerine gerçekten araştırma yapacak çok şey çıkartmış oldu. Herkese tekrar teşekkür ediyorum bu geç saate kadar takip edenlere. Görüşmek üzere diyorum. Kapatıyorum. Tekrardan teşekkürler. Görüşmek üzere.